Hi, I'm Brandon Gracely. I'm a high school math teacher. We're going to look at the inverse trig ratio functions today. They are sine inverse, cosine inverse, and tangent inverse, or we'll say sine inverse, cos inverse, tan inverse. There are other ways to write these, but I like these ones, and that's what my calculator shows, so that works out nicely. Remember the regular trig ratios, sine, cos, and tan, those take in an angle, like sine of 45 degrees, and when you type those in like this, you say 45 sine, and it gives you a value like this. And you can write that, well, there's a bunch of ways to write that. I'll write the decimal out right now. That one's a nice one, though. And so every one of these takes an angle and gives you back some ratio, some relationship between sides in a triangle. These ones take a ratio and give you back an example of an angle that would give you that ratio. Okay? So, for example, if I take that value that I just had, and I use my sine inverse function on this calculator, on the iPhone, I'm going to press the second key, and then there it is right there, the sine inverse button. When I press that, it says, oh, 45 is an example of an angle that will give that value. Sweet. So if I say sine inverse of, and you can use brackets or not, 0.707 equals, and then you could say it's 45, or it's about equal to 45 degrees, since I did some rounding there. Okay, so that's how this works. Now, why we have this is that sometimes you have triangles or other things where you know some things about them, but you don't know kind of everything. Let me just make something a little bit accurate here. Okay, so let's say you have a very popular triangle. We'll call it ABC, the 3, 4, 5 triangle. You'll see this one a lot. Pythagorean Theorem, this one works out really nicely. But there's a question. The question is, what are the two angles A and B? We know all the sides, but we can't solve this triangle until we know the angles. So we know, for example, that sine of A is the opposite side to A, which is 4, divided by the hypotenuse here, which is 5. So here we have a fraction, a number, that is this ratio, but we don't know the value that could give us that ratio. So we simply take the sine inverse of both sides. So then A is equal to the sine inverse of 4/5. Okay, so how do we type this on a calculator? I take 4 and divide it by 5, which is 0.8, and then I press my sine inverse function. So I've already got it there. If not, you press the second key to make it available. And when I press it, it tells me that A is about 53.13 degrees. Now I can do the same process for B, and then we'll do a little bit of other math to show there's an easier way. Now that I've got this number, I can do, well, let's do it with cosine. Let's say well, maybe not. We'll do sine again. Sine of B is equal to the opposite side to B, which is 3, divided by 5, the hypotenuse. Okay, so take the sine inverse of both sides and you get B equals sine inverse of 3/5, which is 0.6, excuse me, 0.6 sine inverse. Looks like it's about 36.87 degrees. Now you'll notice right here, see these two values? Those are the two values A and B. 53.13, 36.87 degrees. Those add up to 90. Check it out, they add up to 90. And that makes sense because our triangle has to add up to 180, and 90 of it's already taken up with this value here, the angle C, which is 90. So these two add up to 90. As soon as I knew what A was, I could just take 90 minus A, and that would give me B. I didn't actually have to use the ratio here. Well, could I have found this another way? What if I had used the tangent ratio? Like, what about tan of B? What does that look like? Well, tangent of B is the opposite side, 3, divided by the adjacent side, which is 4, not 5, 4. Okay, that's pretty good. That's 3/4 or 0.75. That means B is equal to the tan inverse of 3/4. That's calculator worthy, right? 3/4, I can do 3 divided by 4, or I know that's 0.75. and then I do second, tan inverse right there. Ah, there it is, same number, 36.87 degrees. All right, pretty good. So we can use these ratios to solve triangles that we don't know all of the angles for. We only know, we just have the right angle. Let's do another similar one. Here's another popular triangle. We'll label this one differently. Let's go D, E, F. And there's the 5, 12, 13 triangle, the skinny one that works out nicely with the Pythagorean theorem. And so once again, I don't know some angles. Let's try the cosine ratio this time. So cos of E, right here, well, I want the adjacent side, which is 12, divided by the hypotenuse. Cos E is 12 over 13. That means taking the cos inverse of both sides, I'll be left with E is equal to cos inverse of 12/13. And so E is equal to, take 12 divided by 13, press the equals key. Now I have 12 over 13 as a decimal, and then I press the cos inverse button to get that it's about 22 point, I'm going to round off to two places here, 22.62 degrees. And now I'll be cleverer, and I'll notice that I can take angle D is 90 degrees minus angle E. I don't really need the angle symbols there. That is, it's 90 degrees minus 22.62 degrees. And you know, this is the kind of place where it's pretty easy to get off, be off by one, making a little mistake here, because this is like a little less than 70. It's pretty easy to make a mistake. So just take this one, and I always hit like minus 90. I'm going to get a negative number there, but it's the positive version. 67.38 degrees, approximately. Okay? All right, those are pretty nice. Those are using some whole number values. What if we have a triangle that has some gross values? For example, what if we have this triangle right here, 6 and 9, and let's label it A, B, C. Well, we don't really have everything. We don't have the three sides like we did for the previous ones. So we can still do this though, and there's a couple of ways. One is to use the Pythagorean theorem to find this side, which we'll do in a moment. The other is to use the ratios that we can use. So for example, if I want to use A, I could take the cosine of A, and that is going to be equal to 9, the opposite to A, divided by 6, the adjacent, 9 over 6. And so that means that A is equal to the cos inverse of 9 over 6. 9 over 6 is actually a pretty nice number, 9 divided by 6, see there, 1.5. And if I take the cos inverse of that value, I got an error. What did I do wrong here? 9, oh sorry, it shouldn't be cosine at all. That should be the tangent. I'm sorry. Tangent, of course. Opposite over adjacent. Tangent. I was wondering how I got such a big number. 1.5. You can't get cosine. You can't use cosine to get 1.5. 1.5 and take the tan inverse. There we go. That's more reasonable. 56.31 degrees. Let me just write that down right here. Okay, and now we're left with finding B is going to be equal to 90 degrees minus 56.31 degrees. And so that'll be 33.69 degrees, about. Okay, all right, so we've now found all of the angles. We have one side left to find, and that you can do that in a few ways. You can use the trig ratios if you like, or you can use the Pythagorean theorem. I like the Pythagorean theorem because we end up with a nice, pretty radical out of this. So we're going to call this side little c, and little c squared is 9 squared plus 6 squared. It's the other two sides' lengths squared. So c squared is 81 plus 36. That means it's 110, 117. and c then must be the positive square root of this, which is, you can write as root 117, or it is root 9 times root 13, I think. 90, yeah. And then root 9 we know is 3, so 3 root 13 is the final value, the exact value for this side c, 3 root 13. Okay, so we've used the trig, the inverse functions for trig ratios to find the angles in some triangles when all we knew were some sides. I hope that helps, and thanks a lot.